الله أكبر الله أكبر.
The mosque, the house of God, where Muslims relight their devoutness, strengthen their relationship with the Creator, meet their Muslim brethren and renew their sense of belonging. The architecture design of mosques can be quite challenging due to its wide range of activities. Moreover, mosque design should be based on cultural and spiritual architectural concepts, where beauty and functionality are combined and mixed with the right ingredients. Therefore, the most persisting challenge in designing a certain mosque is creating a proper space that is suitable for praying and contemplation, and that is only achievable by making the worshippers feel more comfortable and comfy, without neglecting the practicality needed to serve certain purposes or tasks, such as Quran learning or reading. Many mosques are already utilizing latest technologies in lighting, acoustics, and air conditioning designs in order to create that comfort feeling for its visitors. However, these systems can be quite expensive to operate and consume plenty of energy if not designed and used properly. This work is directed into exploring strategies and methods used to create a sustainable mosque without compromising its spiritual effect. The work suggests 6 strategies in order to create an energy and cost-efficient mosque design and operation. The energy modeling software used is CarrierHAP, which is an advanced building modeling software with deep understanding of air conditioning design and operation. Murdif Grand Mosque in Dubai was selected to be the case study of this work. The building was designed by Khatib and Alami Consolidated Engineering Company. The construction was finished in 2014. The building is located at Murdif area in Dubai. The mosque has worshippers capacity of 2,477 person. The mosque was built based on Fatimid architectural style and provides several amenities such as ablution area, women prayer space and a parking lot. The mosque consists of a large octagon plan footprint, with a side length of almost 18 meters. The height of the mosque is almost 9 meters. The mosque has a dome of almost 10 meters diameter. The first thing needed to understand the energy consumption of Murdif Mosque was to get the energy bills for year 2018 from the Islamic Affairs Charitable Activities Department in Dubai. The bills were studied carefully and used to make initial calibration between the actual energy consumption and the calculated energy consumption of the year 2018. The calibration showed a good agreement in most of the year months, except for the month of June, where the actual consumption was much larger than the calculated. This can be due to Ramadan month coming at the month of June 2018. Another disagreement was found in the month of December. No more information are available to explain this disagreement, except that the air conditioning system might be switched off during this month. Then, the energy budget for the building was studied to check the highest and lowest energy components contributing to the total energy consumption of the building. The air conditioning system was found to be the major contributor to energy consumption by a percentage value of 75%, followed by the lighting system with almost 19%. The plug load share was almost 4%, and the water heater's consumption was less than 2%. Hence, the work chose to focus on air conditioning strategies, both passive and active, as well as solar water heating system, to lower the annual energy consumption of the building. The argument for this selection is that air conditioning makes most of the building energy consumption, and saving 15% of air conditioning consumption, which is achievable, is almost the same as saving 66% of the lighting system, which is almost impossible. 4 air conditioning passive strategies were used to lower energy consumption of the building. The first one is building air tightness and infiltration. The second one is windows glazing. The The third is windows shading utilizing Arabic lattice shading devices. And the fourth is wall construction and insulation. The fifth strategy is using a solar water heating system instead of electrical heating system. And the sixth and final strategy is an active air conditioning approach, utilizing a smart controller. Designed by Fuzzy Logic MATLAB software, the new controller will be programmed to address the prayer schedule, population of worshippers, climate and temperature differences, in order to operate effectively and efficiently. Fresh air can enter the building in various methods. Such methods include natural and mechanical ventilation, open doors and windows, and cracks around building openings, which is called infiltration. Infiltration has a significant effect on the heating and cooling load of the building. Air movement through building openings and cracks is controlled by the pressure difference between inside and outside the building. Building's pressure at ground floor in cooling seasons is usually mechanically controlled by the HVAC system. The value of the pressure varies with an average of positive 10 pascals. Ashri Handbook Fundamentals 2001 provides a method of calculation of infiltration, called the crack method, which is given by infiltration rate in cubic meters per second equals to constant multiplied by the crack area multiplied by the square root of the pressure in pascals. The building initial load calculation is based on an infiltration rate of 1 air changed per hour. This means that the air inside the building is going to be fully changed each hour. This value of infiltration is usually assumed for commercial buildings. However, lowering this value is possible but limited to the proper and precise calculation of infiltration. Before attempting to calculate the actual rate of infiltration, the effect of lowering the value of air change per hour was simulated using HAP software. The results showed a great impact of lower values of ACH on the building cooling load. Recent advances in windows glazing technologies can limit infiltration to the minimum in cracks around windows, so the focus of infiltration calculation will be on the building doors. The building is utilizing 8 doors with the presence of a buffer zone, or entrance lobby. This limits infiltration to be only due to the cracks around the doors without considering any open door at any time of operation. This is a typical door of the mosque. The door leaves a 90 cm width and 235 cm height. The crack from the sides and above the doors was measured to be less than 10 mm, while the crack between the leaves was measured to be less than 5 mm. The crack at the bottom of the door was measured to be less than 30 mm. The calculated infiltration rate was found to be 7,740 cubic meter per hour, and the mosque total volume is 15,589 cubic meter. Considering a safety factor of 20%, this gives an ACH value of 0.6. The total savings from using this ACH value on the building total energy consumption was found to be 5.8%. The windows of the buildings are double pane with metal frame, with low solar gain and low E-coating. The windows are having a shading coefficient of 0.39, which is a very good value. The effect of shading coefficient on the cooling load has been studied prior to deciding any changes. The figure shows a limited savings of less than 0.5% when using a shading coefficient of 0.37, while the value increases to almost less than 2% when using a shading coefficient of 0.31. This is due to the fact that a good shading coefficient is already used in the building windows. Hence, there isn't much improvement in this area, except using the actual shading coefficient of this kind of windows with a value of 0.37. The energy savings utilizing this new value of shading coefficient is almost 0.7%. Windows shading used in this work is the Arabic lattice type, which is used to shade the whole window and allowing sunlight to enter based on the perforation ratio of the lattice. This type of shading can be quite efficient in reducing the cooling load of the building, as well as adding a nice decoration to the outside of the building. Not to mention the effects of light and shadow that influence the inside lighting of the mosque. The effect of introducing Arabic lattice shading to the building windows has been studied prior to deciding which value of perforation type should be considered. The figure shows a good impact of almost 4% energy savings in cooling load for perforation ratio of 50%. This work adopted a lattice with a perforation ratio of 50%. This will lower the total energy consumption of the building by almost 2.6%. External walls are the main boundaries between the inside of the building and the outside conditions. Hence, it mainly affects the heating and cooling of the building. The overall heat transfer coefficient, U value, is a measure of heat loss through building walls or floors. A high U value indicates a high heat loss through the wall or roof section, while a low U value indicates a low heat transfer. The building initial load calculation is utilizing a wall construction with U value of 0.5 watts per square meter Kelvin. This value is good but can be better if the insulation thickness was increased. The effect of U values on the percentage savings in the cooling load was studied prior to deciding a new value for the heat transfer coefficient. The figure shows a good relationship between lowering U value and savings in cooling load. The selected U value is 0.34, which corresponds to a wall section of the base model with an extra of 30 mm of polyester insulation. The total energy savings due to using this new value is estimated to be 1.45%. The plumbing drawings shows that the building is utilizing 2 electrical water heaters with 2.5 kW capacity each for heating water. The new strategy proposes using a solar water heaters instead of the electrical heaters. However, using solar heater does not eliminate the need for electrical heaters as a backup. A successful water heater will heat and store water at a temperature of 60 degrees Celsius in order to get rid of a certain bacteria called Legionella. This type of bacteria thrives at temperatures between 32 to 35 degrees Celsius, while temperatures over 60 degrees Celsius has a bactericidal effect. Hence, solar water heater may not be able to heat water to this temperature, especially at winter seasons where hot water is mostly required. This is why backup electrical heater should be present to cover up for the solar heaters at certain situations. Adding solar water heater will lower the total energy of the building by a value of 1.25%. Mosques are different from any other building. The pattern of use of mosques are quite unique. For example, the mosque is probably empty during the day, except for 5 prayer times where it shall experience sudden populations. This higher population can last for 15 to 20 minutes, then it will be empty again. Moreover, mosques experience very high population on Friday prayers than any other day, and Ramadan than any other month. Most mosques respond to this different pattern by either switching on the AC during the day. The other option is to switch on the AC system just before the prayer, and closing it just after the prayer. The two options are not energy efficient and they don't serve the purpose for AC system, which is basically comfort. The need to design a smart AC system that fulfills a mosque different pattern of use is of most importance. This work is proposing a smart AC system that is controlled using fuzzy logic techniques. The input variables for the fuzzy logic model are inside temperature, temperature difference between outside and inside, dew point temperature, and percentage population inside the mosque, which can be found using a live feed camera, or a customer counter such as counters at malls and hypermarkets. The output of the fuzzy system is compressor and fan speed. The smart system was called SMAC. A software was generated to calculate the compressor and fan speed based on the input parameters and set of rules. The results of the controller simulation using MATLAB were carefully studied. Operation curves have been generated to show the system performance at different situations. Then, the proposed system was simulated using Carrier HAP software. Operation profiles have been generated in HAP to reflect the operation curves from the fuzzy logic system. A typical weekday profile, a Friday profile, Ramadan profile, a Friday and Ramadan profile have been generated in HAP. And these profiles were given their assignment at the right day and month of the year. The results show that the proposed smart system can lower the total annual energy of the building with almost 20%. The final results showed a great improvement in the building total annual energy demand. The 6 strategies discussed in this work were able to reduce the total annual energy demand by almost 30%. The HVAC system annual load, which includes space cooling and fans, was reduced by almost 40%, while the water heater's load was reduced by 70%. The lighting load and the plug loads were unchanged, but their share in the new energy budget was increased as the other components' share was decreased. The total savings corresponding to the new proposed system, and based on Dubai Electricity and Water Authority tariffs for residential sector, is almost 73,500 dirhams. Energy assessment for the building was done using Abu Dhabi Istidama. For the smart system, which was able to save almost 20% of the building annual total energy demand, Istidama gives 4 points. For the air conditioning passive strategies, which were able to reduce almost 13.7 from the annual external heat gain, Istidama gives 1 point. And finally, for the solar water heater, which is considered an on-site renewable energy source and was able to save almost 1.25% of the building annual energy consumption, Istidama gives 1 point as well. The total points that the new proposed model can achieve based on Istidama is 6 points. This work showed that mosques, such as any other buildings, can be designed to be sustainable, without affecting its functionality and holiness. The strategies used in this work, including the smart controller system, are not limited to mosque use. They can be used in any building. However, an energy modeling software with strong capability and precise results should be used in order to properly estimate the outcomes of these strategies.